Right, let's go to 38. Believe it or not, our time is coming to an end. Scary fast, right? So hang in there. So we're gonna go to 38. So this is my plan. I wanna do at least 2 questions together. And at some point today, I'm gonna give you an AC on this. So we're gonna have an AC before we go home on logarithmic functions. And so on top of that, I will give you 2 take-home ACs, right? So those you do over the weekend. So it's almost gonna force you to review. So it's not like it's a disservice. It's actually gonna help you, right? I don't want to waste your time. So you do those. You bring them back on Monday. I will mark those, and you write your quiz. Your quiz is gonna be on chapter 7, pretty much exclusively. I'll sneak in some chapter 6, like the polynomials, but it's not going to be as extensive as chapter 7, exponential and logarithmic functions. All right. So I might ask you to match graphs. I might ask you to, just basic like end behavior stuff of all those functions. A domain and range, perhaps, just giving you a graph. So have that ready to go. And I'm going to also give you. I'm going to have it out here because otherwise I'm going to forget. Dun, dun, dun. Right? This used to be on the whiteboard a while ago. I took a picture of it. So these are like all of our functions with the domain and range and all of that. So you can look at it one by one. It summarizes chapter 6 and 7 for you. All right? So I'll give you that as well. So if you don't know what to do with it, just fold it in half and it becomes basically like a normal sheet of in your notes. If you want to staple it, you can do that as well. All right. Okay, here we go. Let's finish page 38 here. So I ask you to grab your calculators. Yeah, let's enter those the equation again. Okay. So this is a logarithmic equation. Maybe to clarify, when do I use log? When do I use natural log, ln? Just read the equation and just follow the equation, right? If the equation given says log here, you press log. If it's ln, press ln. If you don't, you're going to get a different answer, okay? But if we do a regression, it's always natural log that we're going to get. Next thing you need to do, especially with a logarithmic function, don't let the variables throw you off. Whatever's on the right side is your x intensity, right? Maybe I'll go from this to say, hey, that's my intensity. And whatever's on the left side of the equation is what goes on the y. And look at time. Time is on your y-axis. And that sometimes can cause you to be like, wait a minute, I'm doing this wrong. And students flip the whole thing. And then everything is off. Every answer is off. Everything is wrong. So make sure you don't do that. You were asked to graph this. Before you even start, though, you look at your logarithmic. If you pay attention to this part, sometimes these are flipped. Okay, guys, this is in front. So this is what I mean. If I go with the negative 36 natural log of I plus 266.44, it is a well-known fact. Like if I flip it, it doesn't change anything. Okay, this is still A, this is still B. Like whatever's in front of natural log, I should say, that is what we consider B. Okay, so don't let that throw you off. We know that this part gives us our y-intercept, not y-intercept, sorry, the point 1a. Okay? That's very important. So we know that this is going to be part of our graph. Sometimes it's helpful, sometimes not so much, and I'll talk about that with the other example I do. B is less than 0, so it's negative, right? We notice that B is here or over here, regardless, it's negative. So my equation, right, the graph is going to do this. So you can maybe look at it, it's going to for sure go through 1a, and then from there it's going to go down, okay, like that. We don't know where it's going to cross, but we know that's going to happen. What do we call this dashed line? Starts with an A. You remember? It's the asymptote. Do you remember that? Okay. Just in case. So I graphed it. I will label this one. This is 1 266.44. I think it's good for it to stand out in our graph, right? That helped me to have a bit of a reference. And then I also found the x-intercept, right? This point was right here, 1522080, right? So these two, and then finding something along the way is always a good idea. So if you have your x-intercept and you have that 1a point that is on there, find something in between. It's up to you, but that's going to help you find the correct shape, because this would be wrong, okay? Like some students would just flat out like connect like this, and you don't want that. So we want the general shape to be accurate. So how about I didn't get to it yesterday, so I'm just going to say I'm going to graph it. I'm going to go second trace 1, and I'm going to try 400. It's supposed to be 4859. I'll just state that here. 400 gives me 4859. It's another point I found. And that's right here. 400. I don't require you to label it on a test as long as it goes through where it's supposed to, but I'm going to do it here for you to have it in your notes, right? So you got to help yourselves come up with a graph that looks decent. Okay? And you have the calculator. You're not doing any algebraic work here. You're just plugging in, right? So keep that in mind. Nicholas, you had a good point here yesterday. It's like, isn't years here? Like, why is it like that, right? The example you would have to have taken physics for this, but you know, when you compare acceleration over time, acceleration is velocity over time itself. And then you can yet compare it to time against time itself as well. I don't know if you remember that in physics. I don't know if you've taken physics, it shows up, but if not, don't worry about it too much. You know what? I can tell you this. Just follow the units that you're given, okay? Whatever random, odd, like there's one about earthquakes. What is it that they use for earthquakes? Anybody remember? We'll get to it. I'm drawing a blank, but earthquakes are also measured in a different unit, and so just go with it. Whatever the question gives you, that's what you go with. All right, let's keep going. What is the exact initial radiation level recorded to the equation? Level according to the equation. So we'll say this. Write this down, because this is where, when initial radiation happens, when would you say initial radiation happens? What's your time at the initial, when everything starts? 0, right? Time is 0. Initial radiation happens at time equals 0. In this case, what are we? Years? Is time x or y? It's basically saying, hey, what's x when y is 0, isn't it? Because we've determined that time represents my y variable, correct? So we need to let y2 equal 0, and then we're going to go second trace 5. Did you catch that? Normally time is our x, right? So we would go, oh, it's the y-intercept. No, in this case, it's the x-intercept because time is my y variable. And I already know that, right? I've calculated it when I did my graph. Okay, this is the x-intercept. So initial radiation is 1,522.08 MSV per year. There it is. Oh, this wasn't, was this B? What's the exact initial? Okay. C. How long is it required? That's not my question. I actually took this off of someone else's worksheet. But what time is required to achieve half the initial radiation level? Half the initial radiation. So we're going to go 1522.08, divide that in half, and we get 761.04 MSV per year. That's what we're after. So we want to know if x is this, what is y? That's what we want to know. So what function are we going to use on our calculators? Second, trace 1, x is 761.04. Let's go ahead and find our y. So second trace 1, 761.04. That's 25.21. 25.21 years to get down to half of the initial radiation level. Oh, I'm running out of space here, but we're gonna work with it. D, what's the radiation level after in 100 years? So basically, what's the radiation level when time is 100 years? So we let y2 equal to 100. We go second trace 5, and x is equal to 97.28. This all hinges on you finding the graph on your calculator, right? We already did that yesterday. Like, that's actually extremely important to find your window, a window that works. Where I'm gonna erase the homework section here and just do E right there. I'm gonna try to fit that in. I hope you still have space. Just gonna do this here. E. If a level of 10 MSV per year is considered safe, how long will it take for the contaminated area to be considered safe? So it's saying, hey, if this is 10, how long will it take for you to get to 10? So this is second trace 1, x is equal to 10. And let's see here, it's 182.72 years. That's how long it would take for the radiation level to get to a point where that area is considered safe. Okay. I'm just curious. I'm going to fit that in here. Notice that I didn't label the equation here on my graph. I'll do that yet. But what if I asked you for the domain and range here? Based on the context. I didn't ask that, I know, but my domain here would be, we're talking about the intensity, correct? the intensity. What's the lowest intensity you can possibly get to? It would be 0, correct? Is it ever going to touch the y-axis here? It's never going to touch. So there's a problem with square brackets. But why did you put it in the first place? Right? I know you're asking yourself that. It's because that's our natural tendency. So we actually would have to say 0 to the maximum intensity here is the initial intensity. That's the highest it has ever been, which is 1522.08. That would be square bracket there. And then the range would be for all the way 0, right, times 0. Where do you think this would end? I would say once the area is considered safe. Okay, technically. But we don't, like this context, I didn't wrap the context around it. So technically time just keeps on going forever because this curve never touches it. So we're going to go infinity based on the fact that I use 0 there. So it would have to be very context dependent. Go ahead. Context dependent. Okay. Maybe I'll do the asymptote one more time. Here, just along. You don't have to. Like we're never told that you have to graph it, but you have to know about it. Like the asymptote just means that it never touches it. You guys watch Lord of the Rings? No? You've never watched Lord of the Rings? Okay. There's one. There's a meme out there where Gandalf does the "you shall not pass" with his sword, so the curve never actually touches it. Anyways, so that's an example here for logarithmic. I'll take a quick break before I go on to the next one. I want you to go to 37. Okay, the exercise right here is to match. You're going to be the matchmaker today. Okay? So match these 4 with the graph you think it goes to. So you know what I would like you to do is actually write the equation somewhere around or underneath the graph that it belongs to. So this is kind of mixing up exponential and logarithmic. So take a moment to do that. I'll go over it and then we'll do one more example. So this is what I mean, yes, there's many ways of doing this, I get it. But you should know that this is exponential. This also is exponential. This is definitely logarithmic. This is also, you know what, I'm still calling this a logarithmic, even though it's a natural log. But these are like under the log camp, this is exponential. We know that our y-intercept is 0.5 and that this is what? It's increasing, correct? It's doing something like this. Here my y-intercept is 0.2 and this is decreasing. So this is doing something like this. Okay. Logarithmic, what's going on here? If you need to rewrite this, this is what's happening there. A is just 0. Okay. So you have a 0.10 on here, and B is positive, so you know that this is doing something like this. Just have this on your study sheet and you'll be fine. This is, if you want to rewrite this is 0 minus 2 natural log of x. So you have a 0.10 on there, and because this is negative, this is doing something like this. All right, so without even graphing it, you know, you understand what's happening. So we know that these two are exponential. A and C are exponential. I hope you understand that. How would you know if I asked you, tell me why we know that's exponential? And you're like, well, duh, just cause. I mean, it's like obviously. But you, yeah. the sharpness of the increase. Okay. Okay. What about the fact that they have y-intercepts? Do logs ever cross the y-axis? No. So right there, you're like, these are definitely not logs, right? So that's, I would say that's one of the main things that I want to draw your attention to. So here we go. This one is decreasing. So this one right here is 0.1x. Did you get that? And then C is going to be the other one, obviously. All right, we got that. And this one is decreasing right here. So this is going to be my y is equal to -2 natural log x. And obviously, this is going to be the other one. Y is equal to 6 log x. Okay, so there we have it. If you were able to do this, you're doing pretty good in understanding the differences between the two. All right, let's keep going. So I will tell you this. 39 and on, like there's a bunch of just word problems where I give you the equation and they look weird. I know they look weird, but you can still do it. And then I snuck in some exponentials yet, like 42 has an exponential, right? Question 2 on page 42. So you can practice those. I posted the key to that. We're going to go a little further ahead and go to 46. The nice thing about logs is you don't have to make your own points. Okay, remember how exponential with doubling and half times, you have to make your table. Logarithmic doesn't have that. We're going to give you the points. So this is on page 46. Highlight that. Anytime it's modeling, you're thinking regressions. Okay. So when my wife gets all ready to go out for a date, I'm like, you look like a regression instead of a model. She wouldn't appreciate that, but maybe math people would. Note, when performing a regression, the calculator can only perform natural logs. Okay, very important. Can I say, I'm going to just say it, not lin reg. Okay, this is the a plus bx one. Do not use that one. That is linear regression. That's a linear. You're going to get a totally, that's going to be wrong, completely off, right? So when you state your equation, it should look like this. Okay. Let's do first a question here. The flash on most digital cameras requires a charged capacitor. Do you remember what cameras are? When people actually had like their own camera? Yeah, remember that? I don't know if you're, I'm just being sarcastic here. Some people still have them. The percent charge, which is Q, remaining on the capacitor was recorded at different times T after the flash had gone off. The T5 flash duration represents the time until a capacitor has only 50% of its initial charge. So T5 means 50% left of the initial. T5 flash duration also represents the length of time that the flash is effective to ensure that the object is being photographed is properly lit. Construct a scatter plot of the given data. So we're never gonna trick you on this. If you have a table, you know it's X and Y like that. So let's go ahead and enter that and come up with a scatter plot. I invite you to do this because it's always the window that's gonna throw you off. It's not entering it. Well, I hope not, right? Entering should be. Please take a moment to double check after you've entered. You're not missing a decimal. You're not missing a zero. Okay, 975,310. 196.9, 51, 49. Okay. Let's just do our scatter plot. What do you need to do to have a scatter plot? Plot 1, right? plot 1. I'm going to erase any equations I have in there. I don't want that to interfere. Plot 1 is on. I'm going to do a zoom stat because that will for sure go zoom 9, right? If you had to pick between a logarithmic and an exponential, I think this would be for sure a logarithmic y, because this 100, 0 is the x, it's an x-intercept, right? An exponential never crosses the x-axis. So this would not be acceptable. You wouldn't even be able to do it. I think you would get an error. Let me just try that. I'm going to try an exponential. What? There it is. Yeah, see, you get an error. Domain doesn't let you. So let's go ahead and I'll just say the scatter plot indicates a logarithmic regression is most appropriate. There is an x-intercept. Can't be exponential. Cannot be exponential. So, and then we're telling you determine the logarithmic model for the data. So I'm going to go y equals, but I will go stat, calc, ln, reg, natural logarithmic. Okay, so we're going to go ahead and do that. So stat, calc, it's the 9th option here. I find it very, it's a design flaw that they have them right next to each other, but it is what it is. So second 1, comma, second 2, comma, alpha, trace, y1. There it is. Move the y down a bit. That's 0.46 minus 0. You see how that would turn into a 0.1? So maybe I will do this, 0.0998. Mr. Dirksen, would it have been wrong if I went 0.1? Technically not. The province would have said that is correctly rounded to 2 decimals. That is okay. I will just say this, or just don't forget your x there. Okay. So that's my regression, but obviously my calculator is going to use all decimals anyways, right? That's what's, if you go to y equals, it's pasted in there. Okay. So I want you to now see if the graph works, and I think it will, because zoom, yeah, there we go. Zoom 9 did the trick. However, I want to see a little bit. I always go to my window and I make sure x min is a negative. So -5 or something like that. And my y min also negative. I'm going to go -2 or something like that. Y max is very low. Let's just go 1. That might be overkill actually, given the small values. I'm letting my y max be 1, and therefore my y min, I'm going to go -0.5, because otherwise it's going to show too much on the negatives when it comes to the y's. Let's try this. There we go. See, you see both axes. I would like you to see that to be able to see what happens, right? Use your logarithmic model to determine the T5 flash duration to the nearest 100th of a second. Okay, hold on a second. Let's first make sure we understand what's my x variable here. This is my x variable. So this is charge as a percentage followed by time in seconds. And I'm basing it exclusively on this, right? Charge seconds. So x is this, y is that. So what is it asking me? The T5 flash duration. T5, what does that mean? A charge of, let's look up there. It says it represents the time until a capacitor has only 50% of its initial charge. So T5 means a charge of 50%. And we're going to go and find the time it takes to get to 50%. So that basically means this is 50 and it's asking us for the time. So we're going to go second, trace 1, x is equal to 50. And then we're going to go find our y. That's 0. That would be 0.7. Yeah, if you round it, there's no other way. If you round to nearest hundredth of a second. But notice this, watch up here on the table. There's already 0.07 and it's a charge of 49.54. But we know in reality this is because we round it, right? It's actually 0.0691 of a second if you go more decimals, right? To be very, very specific. Because everything happens so fast, right? When you take a picture. Okay. And if I ask you to graph, so this is where scaling is going to be a trick, right? That you got to be careful with your scaling. Maybe I will, oh yeah, there's a 45 has room for graphing, but we'll first do this. State the domain and range, right? Assume that scenario ends at T5. I would like you, before I move on, let's say that the price is $1,000 if you get this right. So you gotta have some motivation to get this right. There's not gonna be $1,000 though, full disclaimer. Domain and range, if you had to, knowing that it ends at T5, the story ends at T5, what would be your domain and range? If you need to have a little sketch on the side, you can do that as well. So I'll make like a booklet with 100 questions, and all you have to do, the whole booklet is domain and range, domain and range, domain and range. You're gonna be so sick and tired of it. Anyways, I won't do that. So look at what I did here. I know that y is my time, x is my charge. I know that, right? 100% is the highest charge you can possibly have at time 0. That was given to me by my table. And so we know that this point, where did I get that from? I got it right from here. Like 1A is like 1.46. And so I know that from there it's dropping like this. It's not really the most important. The most important is that at 50% charge, like if it's anything less than that, you can't see the person or the whatever you're taking a picture of, you can't see it anymore. So it really, the action goes from here to here. So domain is going to be a charge of 50 to 100. And then my range is going, that's my time. So you kind of go here to here. This is my range. This is my domain. Okay, domain is always here, range is here. So range would be as low as 0 times 0 and as high as 0.07. This logarithmic is probably the hardest one to come up with a domain and range. I'm not going to lie to you, but I hope it helps. Okay. So I will say that if you want to try regressions, it's pages 50 to 54. I'm just going to double check because sometimes I make changes to these booklets. I'm just going to freeze that there. All right. Okay. This is all I had planned. I don't know if you want me to do. Is there any question in the homework that you would like me to do? If you tell me, yeah, please do this one, I do that rather than the AC that I'm about to give you. Nobody? Okay. Don't be scared. I don't bite. 41? You all owe Nicholas a coffee or something. He got you out of the AC. Okay. All right. 41. I'm going to ask you, this is what I first will ask you to do. Type this in and find a window that works. You think you were going to get out easy, right? Get off easy on this one. You need me. But if you need me, I'll be doing the work up here. So before I graph it, okay? I know this is going to go through this. Guaranteed, right? Like this is the number. And it's always 1 with logs. Okay? Think about it this way. It can't be a y-intercept because it never touches the y-axis. Okay, and I know that b is less than 0, right? B is less than 0, so this is decreasing. So think of it this way. If it's 1 whatever, it's going to do this. And at some point touch, we don't know where, but this is what's going to happen. So I graph. Terrible, right? Like my window right now is not good. I'm in the negatives with both. My y max is way too small. I need to go at least to like 250 or 200, right? Because that's where that point is. There we go. Boom. I see my x-intercept. I'm happy. That's a good window. Let's keep going. Make a graph. We've done that. Check. Determine how long it will take to get 50% remaining. Hold on. I would still encourage you to do the following. What are these variables? Where does x go? Whatever p is, that's my x. Okay? I don't tell you that, but that's percentage. Okay? So that's percentage. And this would be years, right? The length of time. This would be time right here. This is actually, yeah. I need to be more specific here, which I'll promise on the quiz I give you way more detail, but it didn't tell you what time is measured in. So we know that x is percentage remaining and t is time in years. And cesium-137 is just, right, an element, and it will just, it happens after the nuclear disaster. It's radiated, and so this is where everything starts. It's detectable around the world, the West Coast, and it starts with an initial percentage of 100%, and anything that radiates will decay over time. Okay, that's the basic idea here. B, determine how long it will take to get 50% remaining. So we know this is 50%, and so we're wondering how long. So we're going to go second, trace 1, x equal to 50. Can I just say something here? You got to be careful with the 50. We are assuming that we're just going to enter 50, not 0.5. But it could be that the question says P is the percentage remaining as a decimal, right? As a decimal. Then you have to be careful. You have to turn everything to a decimal. We're not told that, so we're just going to assume that we're going to enter 50 as is. So you just read carefully. Second trace 1, 50. Y is 30.00 years, okay? How long? So 30 years. Why did you put 0.00? I don't know. I just did that. That's not wrong. We're good. C, how long will it take to get 6.25 remaining? Right, so this is the question. You just go second trace. If we have time, I'll try to graph this because these are tougher to graph. Okay. Y is second trace 1, 6.25, 120 exactly years if we round to 2 decimals. So that's C. D, determine what percentage will be remaining on 22,211. So we just go, okay, you need to just make sure you do that and then subtract 2011 from it. Okay, and that gives you 200 years. Because you can't just enter the actual year, you have to go number of years, right? So we're asked, like, what's the level going to be after 200 years? So Y2 is 200, second, trace 5. We know that this is time, right? That's why I encourage you to do that. Read your equation and then tell yourself, hey, what's what? What's what? This is logs, especially with logs, you got to be careful. Is my window going to allow for the 200? Just barely. So I'm going to increase my Y max just a little bit. Regraph it. Y2 is 200. There it is. Second trace 5. Boom, boom, boom. X is 0.98% will be remaining. Because remember, everything is as a percentage. That's what the question told me. State the domain and range. Given the context, I will give you some more context. I feel like let's write that down here under E. I'll write that down. I'll add that because I don't feel it's specific enough. Assume that it takes 200 years to get to a safe level. So basically, we're going to use D to help us out here. So for my domain and range, is it going to be square brackets? I don't know. I just my instinctively I do that, but let's see here. We know that this is 200 up here, and then we hit the x-axis there. So we need to know what this is. This is going to be 100%. I'm assuming that's going to be 100%, but I'm just going to double check. I'm going to let y2 equals 0. Yeah, there it is. It's 100 at 0. This is 100 at times 0. And this up here I already found that it is 0.98 after 200 years. Because remember, time is this. This is the percentage down here along your x-axis. So for your domain, it goes from here to here. So you got to look at this is your domain. So we're going to go from 0.98 to 100%. That's my domain. For my range, I'm going to go as low as 0, and then it goes time kind of stops here. This is my range. So I go from 0 at the very beginning to 200 years. That's my range. So having a little diagram helps. I know it's not the ideal thing to do on a Thursday. Logarithmics, right? I would like to graph this though. So I'm gonna say it's probably a good idea to copy the graph down. Where am I gonna graph this? It's a very good question. I think I'm just gonna use the bottom here on 41 to do so. I know it's not a lot of space. Find a space on this paper and just make it small or as small as you need to. So I'm gonna make this work for me. Okay, here we go. We have a lot of information, so we don't have to even find too many points right now. This is percent remaining. And I know it's going to be silly, but I'm going to go percentage under it. Why am I doing that? Because it could be percent remaining as a decimal, right? Where I'm going to use 0.5, 0.4, point whatever, but I am actually using percentages. So just to be safe. And this is time in years. And I'm going to go make sure my percentage goes to 100. Okay? So I'm going to go 20, 40, 60, 80, 100. I can do better than that. I can go up by 10. This is 50, 60, 70, 80, 90, 100. There we go. And then time, I need to make sure I get to 200 years at least. So I'm going to go 50, 100, 150, 200. And I will just say this, you have to read the question, like, does it stop? Is this model only valid up to 200 years? Or does it continue, right? We are assuming that it stops at 200, so it's going to be very close to the y-axis. Okay. That I know. And I also have 100, 0 that I already found. I found the x-intercept. And I have a couple points that I can use. Watch up here, 30. When it's 50%, I'm at 30. So this is my 50 line. So I'm just going to go 30 right there. I think that's pretty good already. I also have 6.25. 6.25 is at 120 years. I'm just using previous answers that I already have. And then just go like this, curve, curve, stop. And there's my equation, done. I didn't even use 1a. I could have used 1a as well, but I didn't need to. But I would say 1a and the x-intercept, definitely, like starting points, and then fill in with whatever else you need in between. Okay, so this is my encouragement to you: find points in between to have a pretty good graph. Another tip is look at your equation to know what's x and what's y. And even if you make a mistake upstream, continue. So you're getting marks, follow through marks for everything else. Don't leave things blank, okay? That's it for today. Unless you want me to do one more. We had enough.